For our section 2.3 here, we're going to be looking at a concept that we call continuity. And if you remember, we started out the class with a picture of a piecewise function that had some holes, etc., asymptotes and whatnot. And I'm going to reproduce a similar graph to that now. So with some behavior features here, I'll add in numbers here in a few minutes, but ultimately we've seen a graph like this before, and we know how to deal with this graph in terms of limits at those given points. Okay, and so now what we're going to learn about today is how do we deal with this idea of continuity at a point? What does it take for a function to be continuous at a point? Okay? And ultimately the answer is it has to satisfy three criteria. So if we look at any point on this graph, okay, and let's start with this point right here, okay, and we'll just say for argument's sake that that's negative 3. So we'll say that's negative 2, negative 1. So we'll start with the left side here. So if that's our negative 3, and we want to know, is this function continuous at that point? Okay, so we'll answer the question after I lay out what are the three criteria for continuity at a point. So in order for a point function to be continuous at a particular point, okay, three things have to be true. Okay. First of all, the limit at the point, okay, and I'm going to add a point, and we'll call it C. So our point in question is C, and we're going to say that the limit of our function at point C, okay, has to exist. So one thing that has to be the case is that the limit has to exist at that point. So if you look at that negative 3 point that I have there, let's see, does it satisfy criteria number 1?
Yes.
Does the limit exist at negative 3?
Yes.
Yes. So far, it's continuous at that point. Okay? And it may turn out to be yes for all three, and if it is, then we can say yes, it's continuous. Okay? Number 2 is that f of c has to exist. Oops. Start that again. Has to exist. So f of c has to exist. In other words, the function has to have a value at c. There has to be a point c something. Okay, we have to be able to list the point 1, 2, or 5, 6, whatever the case may be. Okay, f of c has to exist. So if you look at negative 3 again, do we have a function value at negative 3? And if so, what is it? 0. Right? So we do have a function value. So far, we are continuous at that particular point. And the third thing, in terms of continuity, okay, is this. Is that the limit as x approaches c of our function and f of c have to be equal to each other. So those are the three criteria. So let's look and see now at our negative 3 point. Okay, at negative 3, you said we have a limit there, and what we didn't answer the question at the time, but what is the limit at x equals negative 3? It would be 0. You said a minute ago the function value at 3, negative 3 was 0. So therefore, in choice number 3 here, are those two things equal? Yeah, they're both equal to 0. So therefore, it would be continuous at that point.
So those two, the number 3 is just that both number 1 and number 2 have to equal each other.
Correct. Yep. So they not only have to exist, okay, individually, but they also have to be equal to each other, or else we don't have continuity. So let's look at these other points and decide if there's continuity or not. And if not, which one is the violation, if you will. So let's look at the negative 2 point, and we'll start out with number 1. So at negative 2, if we look at our picture there, okay, does the limit exist?
Yeah.
First question. Yep, there's a limit there at negative 2. How about step 2? Does the function exist at negative 2? If so, what would be the y value? Is there a y value for negative 2? No. So therefore, we don't need to even look at number 3 because number 2 is out. Fair enough? So therefore, it is not continuous at -2. Okay. What about at the next point in question, which is this one right here? We'll call it, we'll just say it's +2. So at 2, is our function continuous? Well, let's start with number 1. The limit at 2 has to exist. So what do we know about the limit at 2? It does not exist. So therefore, do we need to go further?
No.
Nope, nothing else matters, we're done. It's not continuous at that point. Alright, so then let's go over here to 3, 4, 5, 6. So at 6, let's start out with number 1 again. Does the limit exist at 6? Okay. If you look at near 6, the two curves are converging on the same point. True? So therefore the limit exists. Okay, does the function value exist?
No.
Yeah, it's right there at 6, 0, isn't it?
Oh, yeah.
Sorry. Alright, so that means that 1 and 2 are good. So far we're good. Okay. How about 3 though? No, the function value is 0, whereas the limit is negative something. Let's just say, for argument's sake, that that's -2 down here. Okay. So if that's -2 there at that spot, okay, the limit 0, or excuse me, the limit's -2, the function value is 0, so therefore this is not continuous. Okay.
So basically, it has to be a closed point that's on the line.
Well, when you say line, you mean curve, though, right?
Like a curve, yeah,
Yep.
like on the.
Yep. Yeah, there can't be a hole or any kind of jump or any of that. We're going to classify what types of discontinuities here in a minute. But ultimately, like I said, mathematically, this is the case. It has to have a limit, it has to have a function value, and the function value and the limit have to equal each other. And if you look at any other point besides these crazy points that I made here, wouldn't that be the case for any point that I pointed at? Okay. Wouldn't right there, wouldn't the limit and the function value be the same? Both exist and both be the same? Absolutely. So what if I told you, what about a parabola? Okay. Where is a parabola continuous? Is there anywhere it's not? No. So that type of function, a parabola, y equals x squared, or some translation of it or whatever, is always continuous. There are no points of discontinuity, as we'll call these points here in a minute. Okay. What about the final point that I made here? Let's say x equals 10. So first of all, does the limit exist at 10? There's an asymptote there? No. So do we need to continue? No. So it's automatically not continuous at that point. Alright. So the points that we mentioned that we said no to are what we call points of discontinuity. Now, it's kind of a little bit of a misnomer with the asymptote because at 10 there's really not a point. So if we call it a point of discontinuity, it's kind of a stretch of the word point, I guess. But ultimately that location of discontinuity, I guess, would be more appropriate for the asymptote one. Okay. Now, like I said, when we want to identify these points of discontinuity, okay, and if you want to, you can follow with me on page 76. There's the different types are listed there, but I'll list them here on our notes as well. We have the first type of discontinuity, okay, is what we call a removable discontinuity. And I'm going to switch papers here, for space sake. So, in terms of types of discontinuities, so types of discontinuities. Okay, one type would be what we call a removable discontinuity. And we saw some of those above. A removable discontinuity would be something of that nature, a hole, okay, or a hole with another definition either above or below. Okay. Those would be considered removable discontinuities. We're going to get to the removing part in a minute and why they're called that. Okay. So for now, we're just going to call them. We're just going to be able to identify them, and then we'll talk about why it's called removable in a few minutes. Okay. So that is one type. Okay, another type is called a jump discontinuity. Very scientific word for math class, right? And ultimately, a jump discontinuity is one like we saw here, where we have something like that, maybe. Okay. So that would be considered a jump discontinuity. The third type would be called an infinite discontinuity. And an infinite discontinuity is going to be coupled with graph-wise an asymptote. So an asymptote would be considered an infinite discontinuity. Like I said, part of our job is going to be to identify where are the points or locations of discontinuity, and once you figure out where they are, what are they? Are they removable? Are they jump? Are they infinite? Okay, and then the fourth possibility is what we call an oscillating discontinuity. And ultimately, the oscillating discontinuity is fairly rare. We don't have too many functions that have oscillating discontinuities. But the function in particular that would be a good example would be sine of 1 over x. If you were to graph the sine of 1 over x, and as you get closer to the origin, okay, ultimately what happens is, you can see the picture there, and they'll draw the picture better than I will. But ultimately it just keeps oscillating, getting closer and closer, but it never stops oscillating as we get closer to 0 here. It doesn't actually go to 0, 0. Okay, it just infinitely oscillates. And no matter how many times you zoom in on 0, 0 here, all you're going to see is the oscillating. Right? So it's never going to come to a particular point. And so therefore that one's called an oscillating discontinuity. So like I said, this is a fairly rare one. We'll have the most experience when we get down here with the other three types, infinite, removable, and jump. Okay. Now, with that said, our job, like I said, is to determine whether or not we have discontinuities and what type they are. So if you would find page 80 with me. And on that page we have our, in our homework problems, I want to look at the directions here, and then I'm going to have you try some of these. So the directions in the first 10 are to find the points of discontinuity and then identify the type. Okay. Now, the way we're going to find those points of discontinuity is by either A, looking at the equation and figuring out, like for instance in number 1, we can see that there's going to be a discontinuity at -2. As we know the nature of that function, we know what's going to be a problem with that kind of function. Okay, so we know that -2 is going to be an issue. So we'd look at -2 in particular, and we'd see what kind of discontinuity do we have. Is it an asymptote? If so, it's an infinite discontinuity. Is it a hole? If so, then it's removable, etc. So we're going to do that for the first part here. We're going to take a close look at those functions. We're going to use our calculator to help us do that, to investigate the points that are going to be problems, okay, find those points and see exactly what we have going on there. Okay, and then in number 11, we have a piecewise function that's similar to the one I drew at the beginning, where we need to answer a few questions about, and that's for actually for all of 11 through 18. Okay. And the assignment says what on this one? It goes 1 through 29 odd. Okay. All right. So just for that first part, what we're going to do is we're just going to go through 13. Okay. So just kind of focus on 1 through 13, and then we'll after that we'll do part 2 of our notes. Okay. So we're going to do just numbers 1 through 13 odd. I'm going to give you about 10 minutes to work on that. You may or may not be able to get all that done. I would probably try a few from the first section and then try those 11 through 18 ones, 11 through 13. I guess you only got 2 in that group, but I would look at those as well in the 10 minutes that you have. So don't spend all 10 minutes on the first part, in other words. All right, so go ahead and start working on that. And like I said, I'm going to give about 10, and then we'll get back together and check out what we got for the next part.